Okay, good evening, everyone. So, myself, Subhankar Vedant, together with my colleague, Dr. Rajbhushan Singh, we welcome you to this webinar in the context of webinar series on Spintronics, what we call as WTS 2020. Today, it's my great pleasure to have my friend, Professor Mohammad Ehesan Ali from Institute of Nanoscience and Technology. So he's working as an associate professor, you may know, at INST, that is Institute for Nanoscience and Technology in Mohali, India. So you may know him. Matter of formal introduction. He obtained his Master of Science from Banaras Hindu University. Then he went to IIT Bombay for his PhD degree and received his PhD in 2007. Afterwards, he has been to several places in Europe and for his postdoctoral fellowships. So for instance, he worked at Uppsala University in Sweden, in Ruhr University in Bochum in Germany, University College London in UK, and in TIFR Mumbai as a visiting scientist before moving to INST in 2015. So last 5 years, he is working intensely on various aspects at INST, and his research interest includes ab initio investigations of molecular magnetism, interface nanomagnetism, molecular spintronics. I think this is one of his favorite topic. Magnetostructural dynamics of bimolecular systems, development of density functional theory, broken symmetry, spin constraint, DFT, theoretical spectroscopy, ab initio molecular dynamics, and so on, and various other electron and spin transfer processes. So with this brief introduction, I request Professor Ali to start his webinar. So we may have some new participants. So just I like to mention that during our lecture, we do not take questions. However, feel free to write your question in the chat window. And if you have any question also you want to ask at the end, please write it. And at the end of the lecture, we will take all the questions one by one. So with this, I request Ehesan to start his lecture. Thank you.
Yes, thank you, Professor Vedanta, for this kind introduction. I'm going to talk here about our research activity, mainly on organic molecular magnetism and molecular spintronics that we'll cover explicitly in this talk. Yeah, now it's fine. I'm from Institute of Nanoscience and Technology. It is located in Chandigarh, Mohali, and this is only 250 kilometer northern side of Delhi, and it's located in a very nice place. So I would like to invite all of you to visit some point of time to this new institute. This institute is functional from 2013 only, and we are still working from the transit campus, and we already have got our brand new campus that will be moving by end of this year, and we have already started our moving process. Okay, so this is my group, those who are working on various aspects of molecular magnetism, including the biomolecular magnetism. That part I'm not going to cover in this talk. Here I'll especially talk about Prablin's work, Asima Bajaj and Vishu Chakra's work in this talk. So it's a general outline of my talk. The first I will give an brief overview of the different type of magnetic molecules, and then how to tune the magnetic properties by tweaking the chemical structure of these molecules. And then I'll talk a little bit more about the one of the magnetic molecules that are recently several excitement going on, that is Blatter space radical. And then we will talk about how to induce the long-range magnetic exchange interaction in organic molecular magnet. And then we will use this magnetic molecule in the lead and for spintronic purpose, and we'll see that how quantum effect can control the spin transport across the molecule. And then various porphyrin substrate interaction. And then finally, I will talk about the interaction between a non-magnetic C60 molecule with a paramagnetic interface. Okay, so there are two types of famous magnetic molecule. The one is that transition metal base. Here, the magnetic property arises exclusively from the unpaired electron in the d orbital, and this is quite convenient because we can have the unpaired electron in the d cell. But the second type of molecule, these are pure organic molecules. These are without any metal atom, but still we can see the magnetic properties, and these magnetic properties are quite robust. It is not kind of accidental or instantaneous magnetic properties. So, and more interestingly, these materials are room temperature stable, and one can really use this metal-free magnetic molecule for the various device application. We'll discuss one of the case here, and there is a third kind of magnetic molecule where the magnetization is already aligned to its specific magnetic easy axis. However, in porphyrin case, it is not exactly the case. It shows only the paramagnetic moment, but few other molecules where the symmetry of the orbital plays an interesting role and induce the spin orbit coupling, and that create the easy orientation of magnetization. These molecules are famously called single molecule magnet or single ion magnet. And the last molecule that I'm showing here, it is a C60 molecule. It's called Baki ball. It's like a football. It's an arrangement of pentagon and hexagon, and it is normally it is non-magnetic, but at the interface we will see various exotic magnetic property of this molecule. Okay, now why organic molecule which do not have any d cell still show the magnetic property? That's because of that one unpaired electron resides in the pz orbital. And generally, this kind of molecule are very transient, high energy system. But if we do little bit of engineering of this molecule could be stable at room temperature because of the delocalization. And this organic molecule could be used as a spin, various spintronics application as of porphyrin, because these molecules are also planar as a porphyrin-based molecule. Okay, so this there is a long history of organic-based molecular magnet. It started from more than 120 years back, and various molecular engineering has been done to make it more robust and room temperature stable. And that is the biggest challenge that various organic chemists are working on it. Out of that, I will just give you an overview. Like this is the Blatter radical. This is quite stable. The radical, it has the 3 nitrogen, and the radical center, that what we are seeing in the nitrogen atom, it doesn't localize only on the nitrogen atom. It gets equally distributed in all the 3 nitrogen atom, and that's what provides the stability to the system. And this is a monoradical, and this Sugano et al. They have synthesized dinitron nitroxide. It has the 2 radical centers, and these 2 radicals are ferromagnetically coupled. Similarly, this Rajka's molecule is also quite famous, robust, and it's room temperature stable, and it shows very strong ferromagnetic exchange interaction. Okay. So the realization of solid state magnetic property of this organic solid was not so long. It was done in 1991. And then people got excited about it, and to replace the regular magnet, transition metal-based magnet by organic polymer, introducing many organic radical center. People tried to synthesize, but it has been realized by now that one can increase the number of radical center. But in that case, the cooperativity or the exchange interaction with the radical is not easily controllable because the flexible nature of the larger polymer. Okay, so here I'm going to show that how to tune the magnetic property in this organic molecule. So in this case, here there are 2 radical centered. This is called the metaphenyl connector. So in this position, they are always ferromagnetically coupled. Now, if we rotate this one of the bond, the exchange interaction decreases. So these all have been understood experimentally. And what we do in your laboratory is that we try to compute this exchange interaction, and to do so, we perform density functional theory as well as wave function based theory to calculate this exchange interaction. So what exactly we do? We map that the energy levels obtained from this ab initio calculation, and we fit it. We map it with this Heisenberg Van Vleck energy levels and get the J value. Okay. And however, the task is not easy because whenever we need to calculate the exchange interaction, we need to have the information of the two different spin state. One is the high spin state, the other one is like opposite spin. One can say that ferromagnetic state and antiferromagnetic state. However, calculating the antiferromagnetic state is not so straightforward because the singlet state or low spin state or antiferromagnetic state is a linear combination of several antiferromagnetic states, and this becomes very difficult within the density functional theory approximation, and for that we have to always rely on that multi-reference calculation. And for the multi-reference calculation, it is very very computational resource dependent, as well as it has also limitation to a certain number of atom. We can do it, we cannot apply this kind of multi-reference for a extended material, or we can do only for the small molecules. Okay, so now in my early work, what we have done in this nitrogen nitroxide case. So it has the two radical center, one radical center localized in one side, the other radical center is localized in the other side. Now what we have done, we have increased the distance between the two radical center by incorporating additional carbon atom in the chain. That means, so what we are trying to do, we are trying to increase the distance between the two different radical centers and calculate the exchange interaction. So what we observe that with the length of the exchange interaction, the J is decreasing. This is quite well understood, and this should be the case also. And this was also the experimentally observed case along with our theoretical case. The reason I'm showing this slide, it will be clear in the next few slides. But right now, next slide, I will show that how to tweak the exchange interaction. Now, what I mean to say that the exchange interaction is mainly controlled by the spacer. If we tweak the spacer, the exchange interaction will be could be controlled in this organic molecular system. So here, what we have done, we have incorporated this pyrene dihydropyrene derivative in between the two radical centers, right? And this pyrene is actually a photoactive molecule. So if you shine light, so the bond between them breaks, and then it can recombine thermally again. So incorporating that, what we see that between the two different structures, we have two different exchange interaction. So what does that mean? It means that one can control the magnetic exchange interaction just by thermally or photochemically in this case. And then we again try to find that how the environment could control the exchange interaction in this molecule. So what we did, we kept several ions, because the ion-pi interaction is quite feasible, and it's natural also. In many biological systems, this has been observed that ion and pi system interact. So where we wanted to see that how the ion-pi interaction could control the exchange interaction, and then we find that the J could vary quite a lot by controlling the electron density underneath the ion. Okay, and now also the another way of controlling the exchange interaction, that is called redox dependent. So this is my spacer in between, and then the radical center are localized in the two meta position, and this arrangement gives us the ferromagnetic interaction. However, the chemically, this redox, the spatial could be controlled, and it forms the diketone. This is quinone semiquinone conversion. It is again very redox pair in chemistry. And then what we observed that if we could couple this radical center in this arrangement or probably any other arrangement and change the spacer from quinone to hydroquinone, then again we can control from ferromagnetic exchange interaction to antiferromagnetic interaction directly. Okay, so in between, we are working with experimentalists from Switzerland and ICER Pune. And in that work, what we were doing, that placing two phthalocyanine molecule on top of gold cluster in the gold substrate, and then this gold substrate, these two molecules were placed quite far apart, almost 14 to 15 angstrom apart, and then we find the ferromagnetic exchange interaction. And this is exactly what this experimentalist has observed from XMCD calculation, XMCD measurement, and we find the same thing in our calculation that they are antiferromagnetically coupled. So we have placed some almost like 14 angstrom, looking into the value of 13.97. So this optimized value matches again that STM value, the distance between the two metal center, and we find also the ferromagnetic exchange interaction. Now, what we did, we removed the gold and then we again perform the calculation, and then what we realized that in absence of gold, this magnetic center behave as a paramagnetic. They are randomly arranged in the space. They are not coupled at all. But the moment we bring gold, it shows they ordered antiferromagnetically. Okay, and we found the reason why it is happening. It is happening because of that the conduction electron of the gold are taking participation in the long range communication, and it gives us the antiferromagnetic exchange interaction. So, so what are the learning here, that if we have a conducting medium and then we place the two magnetic centers far apart from each other, and if the magnetic center coupled with the conducting medium, the long range exchange interaction could be found. Now, looking into this phenomena, we try to inculcate this in the organic system. So what we observe in this particular work by Bendikov, so they reported that if we increase the number of benzene ring in linear chain, the system in certain point of time, it converts from molecular state to band structure, and that means it becomes from an semiconductor to conductor molecule. So what we wanted to do, we wanted to use a large N. So we took that N and we incorporate the two magnetic center here, and then we wanted to see whether still we can see the similar kind of long range exchange interaction in this case or not. Okay, now doing so, we find a very interesting and very confusing result. The if you see this curve, so this is like 1 to 10 is the number of benzene ring here. Now, and in the y-axis, we're putting this exchange interaction. Now, and we have done with several density-based method. Out of that, like hybrid functional, we have used PB plus U, we have used constrained DFT. So those are quite sophisticated functional and method in DFT. In all of the cases, we see the similar trend. Now, what is the trend? If we increase the number of benzene ring, the exchange interaction is increasing. Now, sometime back I showed in one of the case that if we increase the number of benzene ring, the J decreasing, and that was observed experimentally, and we also saw that. But the moment we use, instead of carbon, if you use benzene is the spacer and increase the length, that J is increasing. So this is quite a bit puzzling to us. And then we try to see several things. So first of all, we need to check that whether the calculations are fine or not. And then, of course, when we are increasing the number of benzene ring, the degeneracy of the several states are increasing, and that makes the DFT complicated. However, there are different ways to tackle this scenario, and we have applied all the measures. But what we see here exactly that when we are increasing the number of benzene ring, the higher states are coming closer with the lower spin states, and but what we see, the ferromagnetic interaction, the spin is equal to 1. That means those are parallelly aligned. So those are always in the ground state. So there is no doubt that we are getting antiferromagnetic exchange interaction. Apart from the mixing with the higher spin state, we don't see any other issues in calculation of the exchange interaction. And then we check the other level, and of course, we see the degeneracy increasing with increasing the number of benzene rings. And what we also observe, the orbital, which contains the unpaired electron, they are always in the frontier orbital. So this also indicates that everything is perfectly fine. And now what we observe in the next slide, that if we look into the spin density, so what we see, that slight spin density from the spin center is transferring to the spacer orbital, and that is actually behaving as the conducting electron, and that is increasing the exchange interaction in this case. Okay, so we have verified this with Diradical character. These two slides I'll skip. Now with the multi-reference calculation, we tried to find out this. These are complete ab initio calculation based on wave function based theory. It's not density based theory. So these are quite reliable calculations. But what we observe here, that in this calculation, we don't see exact that exponential increase, but it indicates the high J value with the large length. So well, so this is this calculation is quite limited based on the active space. Active space means like uh, the active orbital are involved in the magnetic property, and that we have to count it in this calculation. But as the benzene ring are increasing, so here the active space are increasing enormously. I would say that exponentially. So the larger calculation, for the larger Ehesan calculation, are not quite reliable. Okay, so so the only solution with the de-energy studies, but what we learn from this, that even with the long range, is that a longer policy in cases, we can see the large magnetic exchange interactions. And the reason is exactly the same what we saw using that gold cluster, placing porphyrin molecule placed on the gold substrate. Okay, now I'll move to that Blatter system here. As I already told that in Blatter is one of the most popular radical in the current days, because of that this nitrogen, that radical center is not localized on one of the nitrogen atoms. So it is basically delocalized in all the 3 nitrogen atoms. Now, so this provides a stability to the system, and that theoretically we have calculated the spin density, that popular spin density equal density, but we have also seen some of the spin density delocalizing in this particular ring. So in this work, we given a theoretical proposition how to further enhance the stability of this radical. And what we have done, as we see in this particular ring, that spin density is delocalizing. So what we have done, we have extended with the different benzene ring, so that more spin density will be delocalized along this direction, and then to some extent it will reduce the localized spin density, and it will increase the stability of the system. So that's what exactly we have observed, that if you increase the benzene ring, that the same spin density which was localized on the nitrogen, it is getting distributed along the tail, and this gives further stabilization to the system. Now, this radical was coupled with another stable radical, that is nitronyl nitroxide, and the exchange interaction was found to be quite strong between this radical center and the nitronyl nitroxide radical center, and experimentally the value they observed is around 175. And then we benchmark our calculation in different methods, especially the multi-reference calculation that I was talking about for the larger polyethylene, and we found that the Cassay calculation, that is multi-reference calculation, are quite reliable to reproduce the experimental value. However, if you see the DFT values, the simple DFT, that is that overestimate the J. However, there is a other method, it's called constrained DFT. We also advocate this constrained DFT method. This is again a new method. In constrained DFT, actually we constrain the radical center within the localized space, and we perform the SCF calculation. And this is again a new proposition, and this Cassay and constrained DFT are quite reliable method to calculate the exchange interactions. And based on that, we have proposed several diradical with very high J values, just by putting the Blatter radical and other stable radical that is already known in the literature. And we found that this nitrogen nitroxide and vardigel and phenoxy case, this we get quite high J value compared to the others. Okay, now we also found that not only the position of the coupler, also the dihedral angle of this case will play an important role to control the J. So this is again one has to be very careful, especially when designing a molecule or synthesizing something, that the free rotation, if could be prevented, then the exchange coupling could be controlled. Okay, and we also calculated attached the different nitrogen nitroxide in this different in all these different cases where the radical center is fixed. We are just extending that non-radical part. However, as it is gaining the spin density, the exchange interaction between these two systems will decrease. So it's like that we have taken this scenario that nitrogen, one radical is here, the another radical is here, but we are extending this particular benzene ring. And as the spin density is moving into the density, into the tail, so that exchange interaction reduces between these two cases. And that's exactly what we have observed in this case. Okay, now now we wanted to couple. So far we are talking about the coupling of different stable radical as well as Blatter radical. Now in the literature, when we see that we really don't see quite like strong ferromagnetic exchange interaction just by coupling them. And then we're trying to find that what was the reason. And okay, so before that, I would like to talk about something that as we see the radical center is not localized in one of the particular nitrogen. It's equally distributed in all the three nitrogen atoms. So so that the exchange interaction, what experimentally reported value is actually the summation will summation of all the 9 micromagnetic exchange interactions. So that's what we have calculated for all the cases, and then that individual exchange interaction we calculated and combined based on their weighted spin density, and what we observed at the end, that what experimentally found J value. And why ferromagnetic exchange interaction is not possible in this case, that what we have investigated, all the 9 cases, all the 9 cases means like we have connected A with A, B with B, and C with C. And in the literature, only the one report is there, which is CC connection. And CC connection, and then what we found that the CC is energetically stable, and the two other energetically stable is BB and CC, but all are and will give the antiferromagnetic connection interactions. However, those are the ferromagnetic exchange interactions. These are not energetically stable, and this prediction we published this year. Now we wanted to see that whether this organic radical will have any role in the molecular electronics or spintronics, and to do so, we wanted to place that organic radical in the junction between the two electrode here. There are several reports in the literature where that for the molecular electronics, in this case, if you have this meta connection and put any organic conjugated organic radical, and then what one can see that if you put in the meta connection, you will see that destructive quantum interference. But if you see in the para connection, you will see the constructive interference. And this exactly that in case of benzene, if you have this green and blue connection, you will see that constructive if you are putting in the meta position, you will see that destructive interference. So this is the constant connection. Now we are changing that. If we are putting the meta connection, you will see this kind of feature. That is the feature of destructive quantum interference. But if you are putting in the para position, two lead in the para position, those will have the constructive interference. And this, there are several studies already reported with the pure molecule. I mean, simple molecule. But we wanted to replace this molecule, and then with the magnetic molecule, and we wanted to observe that what are the scenario we could observe over there. Okay, so this is our calculation again. So we have increased the number of benzene ring, and then we exactly observe that what is reported in the literature. If we are having the para connection, then we see the constructive interference, and we if it is the meta connection, we see the destructive interference. And we don't see it when we have the smaller benzene, smaller system, and that we have found that the interaction between the lead overpower in this case, and then it is very difficult to get the pure destructive and constructive feature in this case. Now, this is our simple pentasene molecule. If we have the simple pentasene molecule, we see the upper spin and current and down spin current, they are exactly overlapping with each other. But the moment I put a radical center, this feature goes different, like they are now separated. So this magnetic molecule will give us a spin polarized current, and this is quite evident. And what we observe here, for the meta connection, we are seeing destructive point of interference. And for the para connection, we are seeing CQA or constructive interference. Because so this is as per the rule. Now, the moment we are putting it the radical center, the scenario completely get reversed. In one case, like in meta case, which was having earlier the CQI, now it is one of the spin is showing that destructive interference, and in meta connected, both are having the CQI. And this was again a bit puzzling, but one thing is like we see the spin polarized current, and then we investigate again further and with different other system, and we always see that constructive and destructive interference, but this is the anomalous feature. Okay, and now we look into the frontier MPSH orbital, and we found that there is already this could be explained with the feature if we are having the same sign of this the connecting atom, we will see the DQA feature. If they have the opposite sign, that we always get that constructive interference. And applying these things, we see that the scenario get reversed. The molecular orbital picture get different when we are putting the radical center, and that's the reason that we are seeing that completely reverse behavior in this case. Okay, now so from this. Okay, so this work we published recently in JPC, and what we have learned from this previous case, that to get the spin polarized current, we need to have the radical center. Then again, we went back to the chemistry literature, and then we have found several molecules which are the photoactive. So if you have peroxy bonded molecule, this is already synthesized and quite well-known molecule. If you shine light, this oxygen-oxygen bond that will be a break homoletical scission, one can see, and it forms the diradical. And yeah, it can reconvert into this again the oxygen-oxygen bond. But the thing is that we can utilize this scenario, like if we are having the simple oxygen-oxygen bond, if you see that high spin and low speed, and spin polarization is completely zero, high spin, low spin, the transmission spectra are overlapping with each other. However, the moment you one side light, the photochemistry occurs, it generates two radicals, and that because of the radical, the transmission channel get modified, and then alpha electron and beta electron, they move differently from each other. Okay. Okay, so this is the molecular part. Now I'll move a little bit to that molecule substrate interaction. Here the things are quite predictive, because the earlier case, the organic radical, the site of the radical localization is not a simple specific site, it's over a region, a molecular space. But in this case, the magnetic moment mostly localized only on the transition metal atom, and then we have very less chance to modify this spin moment, but still there are several other ways to modify the spin moment of the central metal atom, and with that modification we can also modify the spin interface that quickly I'm going to go on. Like, okay, so when a porphyrin molecule or phthalocyanine molecule which has that two unpaired electron in the ground state and a spin 2 mu b that generally we see that when the molecule is deposited on the ferromagnetic cobalt substrate, the magnetic moment on the iron get oriented and then because so spin-spin interaction occurs with the substrate and we get the ferromagnetic exchange interaction. And then one of our colleague, experimentalist colleague, what they did they deposit one monolayer of oxygen on top of cobalt, and then deposited the iron porphyrin on top of oxygen, and immediately we see the change in exchange interaction. So earlier it was reported the ferromagnetic exchange interaction. Now if we have one monolayer of oxygen and we deposit the iron, that exchange interaction get modified. So from ferromagnetic to antiferromagnetic one can get. Okay, now so we also find that the interaction between the molecule and substrate are not same always, and this is again the basic surface chemistry. Any molecule could absorb on the substrate in the two ways. One, that the mixing of the electron density between the molecule and the surface could occur. The other case, they are not mixing at all. They are just stacking on top of each other due to the non-covalent interaction like van der Waals or any other non-covalent interaction. Could held them together. Now we showed in our calculation that the molecule, the porphyrin molecule on the cobalt could absorb in the two different surface state. In one case, where it is the electron density mixing quite strongly, and the other case it is just like van der Waals, and then we found the two different minimize the potential energy surface, and then we see the different magnetic change in magnetic moment and the exchange interaction over there. But in both the cases, we see the ferromagnetic interactions. Okay, now for spintronics cases like organic, this metal organic molecule are semiconducting material, and then when they are deposited on the ferromagnetic substrate like cobalt, and then there is a possibility that electron or spin, we are more interested about the spin injection. Spin injection means the specific either alpha or beta electron to be injected rather than both in the orbital of organic semiconductor. So this is the general scenario when they are interacting in very specific fashion, that only the beta electron or alpha electron overlap is happening then the molecule or the semiconductor will get magnetized from the substrate itself. Okay, for this we seen that manganese thallocyanine piece when we deposit it in the cobalt, and we see okay, so for the manganese, it was very strong interaction. We just saw that strong overlap, but when we are putting the copper on cobalt 001 surface, only one of the dx square y square orbital of the copper is interacting with the substrate, and because of its position near the Fermi level, it gets occupied by the only the beta electron, and it shows a spin polarization, and this is what experimentally also it was observed. Okay, now there is other scenario with the porphyrin substrate interaction. So here we have the octaethyl porphyrin deposited on the gold. Now, if you heat after deposition, there little bit surface chemistry occurs, and then the octaethyl arms they lose to hydrogen, and then it's combined with the other, and it form benzene ring. So now it becomes that tetrabenzoporphyrin, and then experimentally a colleague measured that the difference in magnetic moment, and then we accounted that, but how the magnetic the magnetic properties or the orbital, basically the orbital occupation changes due to this surface chemistry itself. This is again that when it is in octaethyl porphyrin, the molecule are not planar on the substrate, and because of that, only if you heat that, it loses the hydrogen, it's form a planar molecule. Okay, I'll skip this. Then there is other case. Yes.
Could you kindly please finish in 5 minutes?
Yeah, I'm almost there.
Thanks.
Yeah. Okay. So in this case, what happened when we are depositing the cobalt on copper? So our copper 11 or 100, we see the loss of magnetization here, and this is experimentally also observed. So the point is here, like when we form a interface, the electron reorganization happens at the interface, and that interaction completely system dependent, and it changes the magnetic property of that spin interface. So in all this case, that all the interface case that I discussed so far was like both are are having the magnetic properties. Now here a work that I'm doing with Professor Vedanta from NICER and organizer of this talk. Okay, so in that work, what they are doing, they have deposited C60 molecule on cobalt, and trying to understand that how this interface is changing the magnetic texture of the material, and that's what we are trying to understand what is happening here. So we have investigated the two different most probable like surface here, and then we have tried to understand that how this interface are constructing. Uh, 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 so all this C60 molecule has two different kind of ring. One is benzene, one is benzene, the other is pentagonal. One benzene is hexagonal. The two ring, and then when we are depositing on the substrate, so what kind of interface it is forming. So this is the first scenario that we try to understand, and then what we realize that uh, it is neither pentagon or hexagon are preferring site to absorb, rather the interface between pentagon and hexagon are depositing on the substrate. Okay, now when we look into the spin density, overall spin density into the system, what we observe that the C60 molecule, which was completely non-magnetic originally, now at the interface, they are getting magnetized. In all the cases, we observe that the interface is getting magnetic. Now, the interesting part is that so that the magnetization density is different, opposite to each other. This indicates that it is antiferromagnetically interacting with the substrate. And why it is happening? So to do so, to understand this, what we have also investigate the electron transfer or charge transfer at the interface, and what we find that charge delocalization is occurring in the interface, and that and how it is happening? It's happening like the majority spin density electron is moving away from the from the C60, and like slightly the beta electron is going from the other direction, and it is creating an imbalance. But interestingly, it is getting antiferromagnetically coupled at the interface. And so this is the scenario is happening, but the case is far more interesting. It is not only only they are antiferromagnetically interacting. The several other things is happening here, like when it is getting bonded, the magnetic moment of the bonded atom is decreasing, and we see that the different surface magnetization between the different cobalt atom, that is also changing because of this charge delocalization. So normally we see the surface cobalt atom 1.8 mu b, but those atoms are bonded, they are decreasing to 1.5 to 1. Okay, and one more thing we observe that the J between these two cobalt surface cobalt, when nothing is absorbed, it is like 661 millielectron volt. But when we are depositing this C60, that the exchange interaction is also changing, so that there is already having a difference in nature of exchange interaction on the surface. And one more thing, we are also observing that the gaining of magnetic moment cobalt is it's not like paramagnetic nature. it has like the magnetic anisotropy. We checked, and then what we observed that the cobalt magnetic anisotropy is also increasing along the perpendicular direction in the spin interface. Okay, with this, I'll just summarize that we have discussed that how to control the magnetic exchange interaction in molecule, especially the photomagnetic control, and then ion-pi interaction, redox control. We also mimic the long-range exchange interaction in organic species, and then we use the organic molecular magnet to create the anomalous quantum interference effect in molecular spintronics, and then molecule substrate interaction to control the interfacial magnetization. And with this, I would like to acknowledge my collaborator, student, and of course, the funding agency. Thank you for your attention.
Okay, thank you so much, Ehesan. So, Brad joins me in clapping. I'm sure others want to clap for this excellent talk, and really large variety of research topics from very basic molecular magnetisms, where you want to manipulate the radical structures and linking it to the exchange interactions, and coming to spin interface, which we kind of do. So I welcome questions if people have it. I do not see any right now. So let me just begin with, I think in between you showed some like manganese PC or iron PC on gold. I think Nirmal does similar kind of work.
They have performed the experimental. This is in the collaboration work with Nirmal and Thomas Young.
Yeah. So in experimental case, how was it? Like they deposited it or they like spin coated it? So let me just complete my question. On this slide, you see they have deposited two molecules, manganese PC and iron PC.
Yeah. So they make the 1:1 ratio, and then so that epitaxial deposition that they did it.
So they kind of mixed.
Yes, they mixed, and then when it is deposited and from this, and then when they measure, see it in that surface STM STM measurement, and then we could clearly see that they are arranging alternatively as a checkerboard type.
Okay.
Okay. So from the
experimentally, experimentally they found that they are alternatively.
Yes. So so the whole theoretical calculation is based on this particular distance between the two atoms. So we can, from the STM, we can measure that manganese and iron distance.
Okay.
Okay, and from there only we constructed the whole scenario, and we also see that when 14.02 we get from the optimization, and from the STM they find 13.97. So it's quite close match with this.
Okay, I mean, I might have missed it. It looks very interesting work. And this radical manipulation, so whatever you were showing, like by that you can tune the exchange interaction. Because I'm asking, I'm sorry, I'm not from that field. So the chemists, do they try to approach really or experimentally try to manipulate, and or how is it done?
Yeah, so the thing is that unfortunately very few people are working on the radical chemistry.
Okay.
Because the thing is that it's need I don't know, quite quite dedicated setup or things, but
no, let's say, let me let me reform my question. So this slide, you have shown these two types of compounds which can show ferromagnetic or antiferromagnetic. Let's say
Right.
from an experimental point of view, is it possible to buy these compounds? Any idea? Or you have to really...
That's what I'm trying to say, that so what is there in the literature or as a material, this is the portion is there. Okay.
Okay.
But, so one need to have little bit of engineering here to NO, not NO. So now why NO we are adding here? Because this with the NO, people have already synthesized several material like this.
Okay.
Okay. So these all are available in the literature, but this is our modeling.
Yeah, so somebody has to do it.
Somebody has to synthesize it. Yes.
Yeah. Okay, I understand that. All right, there are a few questions from others. I'm taking that first. Dr. Anirban Panda is asking, for polycene system, you have shown that S equal to 2 state is lowering. It might contaminate your BS state. Do you think that your spin projection formula is able to handle this to give correct J value?
Okay. Yes. So
otherwise you can just look yourself to the chat window.
But I'm not able to see that one.
No, you need to escape from the full screen and then you can go to the chat window and you can see it.
Okay.
At the bottom, you see there is security.
Yeah. So this is quite a valid question.
Okay.
Of course, this is one of the issue. Like as the high spin state are mixing with each other, it is not easy. I was also discussing in the talk that yes, standard like we can get that broken symmetry, that triplet state clearly for all the cases, but broken symmetry state is going to have a proper mixing, large mixing here, but there are spin projection method. It is roughly you can separate it out, but it is not possible to get a 100% correct answer, especially for this case.
Okay, thanks. The second question from Ramesh Babu. Can you comment on the conductivity of molecular magnets, for example, MnPC or iron PC?
Yes, so those are semiconducting material. And so like it is not conducting, and so this is good for this spin engineering at the interface, but yes, these are not conducting, these are semiconducting material.
Okay, thank you. So is there any other question from anybody else? Looks like not. The talk was very clear. So I like to again thank you for your kind acceptance for this webinar in such a short notice, and we really enjoyed your lecture. Yeah, so we'll see. So we wish all the participants and Professor Ehesan Ali a very happy Diwali, and we will have next week, I think, Professor Hari Sirkan from University of South Florida. So see you next week. Please stay safe, stay healthy, and take care. So thank you. Thank you,
and happy Diwali to everyone.
Yeah, thank you. Take care. Bye-bye. Good night.
Yeah, bye-bye.